Welcome back. In this mini lecture, we're going to go over yet another property of stars, their brightness and their luminosity. This is covered in section 17.2 of your text. But before we get to that, let's talk a little football. Now, I know not all of you like football, but here's our football rankings from this past week, or now a couple weeks ago. But we'll assume that it's up to date and correct. So if you look at these rankings and I ask you which team is the best, would it be Alabama or Texas Tech? And I think most of you would realize that, hey, Alabama, because it's number one. And let's also assume that these rankings are correct. If I highlight two teams, let's say A&M at number 15 and Toledo at number 23, which team would win? And the answer should be A&M because it's ranked higher. So notice that higher ranked teams, the teams that we think are better, have smaller numbers. So we consider that the number 15 team is better than the number 23 team. Now Toledo fans may disagree, but if we assume these are correct, a smaller number means a better team. We have a very similar system in astronomy, and for telling us the brightnesses of stars. This system came from the ancient Greek astronomer Hipparchus, who ranked all the stars in the sky on a scale from 1 to 6. He ranked the brightest visible stars as number 1 and the faintest visible stars as number 6. And just as if we would say that a higher ranked football team has a lower number on the scale, so a brighter star has a smaller number on the scale. Now, astronomers have adapted this scale. It was used for thousands of years, so it's been adapted to modern usage. But because we like to have a mathematical description of any number that we use, we've put it on a scale. First of all, we've kept the idea that smaller magnitudes mean brighter stars. So a smaller number is a brighter star. But we've also realized that 1 was not good enough, that there were stars brighter than a 1 on our new scale. So we've added 0 and then negative numbers. And a negative number is brighter than a positive number. And the more negative it gets, so like a -10, is brighter than a -1. We've also decided to use the star Vega, which is visible during the summer sky, as our reference star, and we're going to give it a magnitude of 0. And in order to make things work out like Hipparchus' scale, so that the brighter stars tended to be around a magnitude of 1 and the faintest stars were around a magnitude of 6, we set it up so that a difference of 1 magnitude is a factor of 2.5 in brightness. So Vega's magnitude 0, a star of magnitude 1 is 2.5 times fainter than Vega. And a star of magnitude 2 would be 2.5 times fainter than the star of magnitude 1, which itself is 2.5 times fainter than Vega, so these start multiplying together. And the way that the multiplication works out is a difference of 2.5 magnitudes is a factor of 10, and a difference of 5 magnitudes is a factor of 100. Now, I'm not going to be asking you to do this mathematics, I just want you to know sort of where it comes from, and to know the basic scale that smaller numbers mean brighter objects. So here are some example apparent magnitudes. Apparent magnitudes just means how bright the star appears in the sky. Vega, as we said, is 0. Polaris is the North Star. Its magnitude is 2. So it is 2.5 times fainter than that magnitude 1 star, which is 2.5 magnitudes fainter than Vega, or something around 7, 8 times fainter than Vega. So Polaris is not the brightest star visible in our night sky. In fact, it's getting into the second tier of stars. The Sun has an apparent magnitude of -26.7. And that's because it's bright. I mean, if we go out when the sun is up, you can't see the other stars because the sun's brightness just overwhelms the rest of them. So how much brighter is the sun than Vega? Well, we see, okay, -26.7. We know that each factor of 5 is 100 times brighter. So a star of magnitude -5 would be 100 times brighter than Vega. Star of magnitude -10 would be 100 times brighter yet, or 10,000 times brighter than Vega. -15, 100 times brighter yet, which would be 1,000,000 times brighter than Vega. minus 20, 100 times brighter yet, so now we're up to 100 million times brighter than Vega. Minus 25 would be another factor of 100, and I think we're now up to 10 billion times brighter than Vega, and then a little bit more than that, another factor of about 3.5. So the Sun appears about 30 billion times brighter than Vega in the sky. Now, how faint can we go? Well, the eye alone can get to about magnitude 6.5. It depends on how dark the sky is, how long you've allowed yourself to adjust, how clear the weather is. But magnitude 6.5, that's about 300 times fainter than Vega, because 5 magnitudes would be 100 and then another magnitude and a half. Now, a 10-inch telescope like what we have out at the Commerce Observatory, which I hope you'll be able to see one of these times, it can see to a magnitude of 16. So that's 100 times 100, that's 10,000 times fainter than the eye alone. So this is why telescopes, one reason they're useful, they collect a lot more light, and so you can see much fainter than that. The Hubble telescope can go down to magnitude of 31.5, which means that the Hubble can see stars fainter, that are as many times fainter than Vega as the Sun is brighter than Vega. In fact, this Hubble telescope can go another factor of 100 fainter than the Sun is compared to Vega. I mean, it's just ridiculously faint. And Vega is so bright that we can't point at it with the Hubble telescope because it would hurt a lot of the instrumentation. So, now it's your turn. Take a minute here and tell me which of these two stars would look brighter from the Earth. All right, have your answer? I hope that you answered A, Rigel, because it has a negative magnitude. Spica has a positive magnitude, so that means Rigel is brighter. However, Spica is actually 1,000 times more luminous than Rigel. If you remember back to chapter 3, luminosity is the total energy output. It's sort of like the wattage. And Spica puts out 1,000 times more energy than Rigel. How can this be if Rigel appears brighter to us? Well, the answer is that Spica is much further away from the Earth. The more distant a source of light is, the fainter it appears. So let's say you're out on a dark night and you see a light off in the distance. There may be a few different things that light could be. One is it could be a kid riding a bicycle coming toward you, and that's the headlight of their bike, and it's dark enough you can't see the bike, but bike headlights are not all that bright, so you may want to think about getting out of the way. Or maybe it's a monster truck headlight and the truck's a mile down the road and they've got their high beams on. And so you've got plenty of time to worry about whether you need to leap out of the way or not. Or maybe it's a spotlight over in a neighboring town, just happens to be shining your way and it's not coming your way whatsoever. So how do you know which of these it is? Because to your eye, all three of these lamps, the bicycle lamp from a bicycle that's about to run you over, a high beam on a truck that's a mile away, or a spotlight in a neighboring town, they all may look the same brightness to you, but they're drastically different distances, and that also means that they're drastically different things. And if we want to know what stars are, we need to be able to sort this out, which is which. If we know the distance to a star, and if you remember back to Minilecture 1, we have a way of determining distances to at least some stars, we can determine its total energy output. The reason is because of something called the inverse square law. Basically, as light gets further away from a source, it spreads out, and it spreads out so that the apparent brightness, the F in this equation, depends on the total brightness of the light bulb, its luminosity, that's the L, and then the distance, the D in the equation, squared. So if you double the distance, the amount of light that you would see goes down by a factor of 2 squared, or 4. If you triple the distance, the amount of light you see goes down by a factor of 3 squared, or 9. This is what's called the inverse square law, and there's a video that I've linked to on the week homepage that illustrates the inverse square law a little better. So if we know the distance to the star and we know how bright it appears, we can calculate how bright it actually is. And that's a useful piece of information in trying to determine what kind of a star we're looking at. Now, astronomers, we use two types of measures for these two different types of brightness. How bright a star appears to us in our sky is called the apparent magnitude. That's the one where we use Vega as a 0 point. We reference everything to Vega. And so apparent is how bright the star appears. If we want to talk about the luminosity, then we use something called an absolute magnitude. And an absolute magnitude is related to the luminosity, and it's a measure of how bright the star actually is. So let's talk for a bit about how we can determine what this absolute magnitude is and how it's calculated. We can see an example of how we would worry about absolute magnitudes and apparent magnitudes in the constellation Orion. Orion is up during the winter time. It's got two really bright stars, Betelgeuse, which is the reddish star at the shoulder of Orion, and Rigel, which is the bright white star that is one of the knees of Orion. And you see these are different colors, and so we know from chapter 3 that they're different temperatures, that Betelgeuse must be cooler than Rigel. But we don't know, although they look about the same brightness, Betelgeuse is just a hair fainter than Rigel, we don't really know which one is brighter because we don't know how far away these stars are. Maybe Rigel is really close and it's an intrinsically faint star, and Betelgeuse is really bright but far away, or vice versa. Maybe Rigel's a super bright star really far away and Betelgeuse is just a faint red star close to us. So what we as astronomers do once we measure distances to stars is we imagine that we magically move the stars to the same distance, to a distance of 10 parsecs. Because if they're all at the same distance, then any difference in how bright they appear is actually a measure of how different in brightness they actually are, which star is putting out more energy. But that's only true if they're all at the same distance. So we imagine that we move them all to the same distance, to the same 10 parsecs, which is 32.6 light years, and then we compare their brightnesses using the absolute magnitude. So an absolute magnitude is how bright a star would appear from the Earth if we magically move the star to this distance of 10 parsecs. That becomes sort of our comparison distance. And so if we know the absolute magnitudes of two stars, then we know which one is actually putting out more energy. So here are some comparisons. We'll start with Vega. Vega's apparent magnitude is 0. Its absolute magnitude is 0.5. Vega's a little closer to us than 10 parsecs, so if we move it to 10 parsecs, it gets further away. If it gets further away, it's going to appear to be fainter, even though it's giving out the same amount of energy. And so its absolute magnitude becomes slightly fainter than its apparent magnitude. So if Vega were exactly 10 parsecs away, its absolute magnitude would be 0.5. The Sun has an apparent magnitude of minus 26.7. It's tremendously brighter than Vega in our sky. But that's also because the Sun is tremendously closer to us than Vega is in the sky. If we move the Sun to 10 parsecs away, it would have an absolute magnitude. If we move the Sun to a distance of 10 parsecs, its magnitude in the sky would be 4.8. So that's its absolute magnitude. And that would be a relatively faint star. If the Sun were 10 parsecs away from us, it would be just a fairly faint star that you could only see on a really dark night and no one would think anything special about it. And then now we can compare which star is actually brighter, Vega or the Sun. If you look here, if both stars were at 10 parsecs, Vega would be brighter than the Sun, so that means Vega is putting out more energy than the Sun by quite a bit. Let's finally look at the star Spica. The star Spica is up in the spring sky. It's a relatively bright star with an apparent magnitude of 0.9, but we see that with an apparent magnitude of 0.9, it appears fainter than Vega in our sky. But if we were to move Spica to a distance of 10 parsecs, it would be extraordinarily bright. It would have a magnitude of minus 3.3. So the absolute magnitude of Spica is brighter than the Sun and then Vega, which means that Spica is intrinsically a brighter star. It's putting out more energy than the other two, even though in our sky, Spica is the faintest of the three stars. So I'm going to ask you a couple questions here. I want you to just think about the answer, come up with an answer before I give it to you. Which of these stars would appear brightest in our night sky? To determine which star appears brightest in our sky, we use the apparent magnitude, and the smallest number is the brightest star, so that would be Vega. Vega would appear to be the brightest star in our sky. Which star is actually the most luminous star? Which star is putting out the most energy? Hopefully you chose Betelgeuse. If we want to know which star is putting out the most energy, we look at the absolute magnitude, and the brightest star among the absolute magnitudes, which would be the -1, -5.6 is really bright, so Betelgeuse is the brightest of these stars in terms of putting out the most energy. And let's see if you remember anything from the first mini lecture. Which of these stars is the closest to the Earth? If you remember from the first mini lecture, we can get distance from the parallax. That's the angle that a star appears to move. The bigger the angle, the closer the star is. So out of all of these, the closest star is star D, which has the exciting name of GL725b. That's just a catalog name. But it's the closest out of all these stars. But you also notice that it appears the faintest, and it actually is the faintest of all of these stars, which tells you that this is intrinsically a very faint star. So that completes this mini lecture on the brightnesses of stars and the magnitude scales. Please go and complete the mini lecture review, and we'll see you in mini lecture 3.